Okay, so let us begin. So, we were talking about primary decomposition. So, as A be a Noetherian ring. So, the results that I proved yesterday, the uniqueness and some of the results, we only need primary decomposition. Once the primary decomposition is assumed, you can go ahead and do that. Prove. So, for example, if you look at the I think 5th chapter of Athia MacDonald, there once the ideal is decomposable and has a primary decomposition, then so they assume this and then go ahead and prove a lot of results, which we discussed here in the Noetherian setting. So, many of those results do not really require Noetherian property, but in Noetherian property the primary decomposition is assured. Once the ring is Noetherian, every ideal has a primary decomposition. Therefore, all the results that was discussed assuming a primary decomposition of an ideal is valid. Okay. So, let A be a Noetherian ring and I equal to intersection q I from 1 to n be a minimal primary decomposition. Let P I be the radical of Q I. Suppose S is a multiplicative set. So, again when we talk about S inverse I, S inverse I we are S inverse I is equal to S inverse intersection Q I. This is finitely many. So, therefore, this is equal to intersection I from 1 to n S inverse Q I. Okay. Now, if S inverse Q if S does not intersect with Q I, this will be a proper ideal, right. Now, the question is whether this will be a primary ideal. Okay. Suppose it is primary, is it true that the radical of this is S inverse P I? So, let us look at one thing. See, S intersection Q I. Suppose, okay, so suppose some S is in S intersection Q I. Okay. This implies that some S power n, S is in Q I. That means some S power n, sorry. I want to say intersection P I. Suppose S is in S intersection P I, then this implies that some S power n is in Q I, but S power n is certainly there in S as well. So, therefore, S power n is in S intersection Q I. Now, conversely, if there is an element in S intersection Q I, that is naturally there in S intersection P I, because that is Q I is contained in P I. So, this is, so therefore, S intersection Q I is non-empty is equivalent to saying that S intersection Pi is non-empty. Okay. The advantage here is that we have a prime ideal. Now, so let us come back to this. Now, first of all, is S inverse Qi. So, assume that suppose S intersection Qi is empty. So, that means S inverse Qi is a proper ideal. Now, why can we say that is S inverse Qi a primary ideal? In S inverse A. So, how do you check that? We want to say every so if you look at S inverse A mod S inverse Qi, every non-zero divisor should be nilpotent in this ring. But what is this ring? This is isomorphic to S inverse of A mod Qi. So, if I look at an element here, let us say x bar, x by S bar, you can write it as some x bar by S where x bar belongs to this. If x bar by S is a 0 divisor here, this x bar will be a 0 divisor here, and that is nilpotent because Qi is primary in A. Therefore, it is nilpotent. The element x bar by x by S whole bar is nilpotent here. Or else you can start with an element x by S times y by t belongs to this. The normal way one can proceed, one can show that it is primary. So, I will leave the exercise to you to check that S inverse Qi is a primary ideal. Okay. Either way one can conclude this. Now, what is the radical of S inverse Qi? S inverse of that again we have seen S inverse of radical of Qi, which is S inverse of Pi. So, therefore, if S do not intersect with Qi, S inverse Qi is a S inverse Pi primary ideal. So, what we have proved is that if S intersection Qi is empty, then S inverse Qi is an S inverse Pi primary ideal. So, therefore, this is indeed a primary decomposition, and if we have to write, so this will imply that if that is a minimal decomposition, I can write this S inverse equal to S inverse Qi, S intersection Qi is empty. I look at intersection over the Qi's which are in the complement of S. Okay. I take this is a minimal primary decomposition. Minimal we have not discussed, but I will leave it to you to check. Minimal primary decomposition of S inverse I. To check minimality, what we need to show is that S inverse Q I do not contain intersection of the rest of them. Okay. That follows from the minimality here. If I am starting with minimal decomposition here, that this will follow. I mean, it is direct verification. Now, as a consequence of this observation, we have another kind of uniqueness theorem. First uniqueness theorem that we proved yesterday said that if I have a primary decomposition of I equal to intersection Q I, then the radical of the primary components is uniquely determined. Okay. Now, so suppose I have a I will write down the statement. Let I be a primary decomposition, minimal primary decomposition of I. And Pi equal to radical of Qi. Okay. So, we have I mean these are all the associated primes of A mod I. Now, among them there are minimal primes, that is isolated primes and embedded primes. So, look at the isolated primes. Let P1 up to PR be isolated prime ideals of isolated associated primes of that means these are the minimal ones. Now, suppose I take SB equal to A, the complement of so SI, I will just write it as SI. SI is A without PI, I from 1 to R. I look at the multiplicative set SI equal to the complement of these minimal associated primes. Then what would be S inverse I? This I mean SI inverse I, this would be, so this is equal to intersection of SI, I mean intersection of SI, let us write this as Qj. But now, this is one of the minimal primes here, and I am taking the complement of this minimal prime. So, this SI will intersect with all other primes, because this is, let us say S1 is A without P1, S1 will intersect with all other prime ideals. Okay. That means S inverse I is equal to SI inverse Qi. That will be the only one that will survive, since SI intersection Pj is non-empty for all j not equal to I. which is equivalent to saying that Si intersection q j is non-empty for all j not equal to I. So, therefore, this will, in this intersection only one of them will survive, which is the primary components which are. Now, forget about this part. If you look at this part, this is, we are taking some multiplicative set. This is independent of the primary decomposition. I am taking, see, we have proved that the primary components are unique, the prime ideals associated to I are unique. So, I take those prime ideals, among them I look at the minimal prime ideals, look at I take one of them and look at its complement and apply the localization. What we get here is S inverse q I. This says that however your primary decomposition is, the primary ideals involved need not be unique, but then the minimal primary the primary ideals corresponding to the isolated prime ideals, they are uniquely determined, right. S inverse q I is now uniquely determined. So, therefore, the second uniqueness theorem says, let A be Noetherian and I be I equal to intersection q I and be a minimal prime decomposition. Well, primary decomposition. Let Pi be equal to Qi, radical of Qi, and let then the primary components, the primary ideals corresponding to the isolated primes are uniquely determined. So, Si is Qi, therefore, the primary components given by phi inverse of Si I, where this is components corresponding to, so let me corresponding to the isolated primes are given by phi inverse of Si inverse of I, where Si is complement of Pi and phi is the natural map from A to Si inverse of A. So, this set has nothing to do, we are not talking anything about the primary decomposition of I when we are describing the primary components corresponding to the minimal the minimal associated primes or the isolated components.
So primary components of what?
Components of S inverse I. Sorry, components of primary components of I. Yeah. So what we are here, see earlier when we tried to prove the uniqueness of the first uniqueness theorem, how did we prove it? We proved that the primes that appear in the as radical of primary components is they are precisely the prime ideals of the form radical of I colon x, where x varies over a, right. So that has nothing to do with the, we have expressed that set independent of what primary decomposition you are taking. So there that is how it is, we proved the uniqueness. Similarly here we are saying that if I take the primary components corresponding to the ideal S inverse I are precisely of this the minimal primes are precisely of this form. So this does not really talk about, because once the primes are uniquely determined we can use that uniqueness to get SI. SI we are not talking about QIs. However your primary decomposition is, SIs are uniquely determined. Now you just look at phi inverse of SI I, where SI is a complement of minimal prime, minimal associated prime. So therefore this implies that so that proves the assertion. This implies that the minimal components are uniquely determined. Okay. So this is another uniqueness theorem. So this one we saw yesterday in the example of x square comma xy. X square comma xy, there was x intersection x square comma y, that was one decomposition, and the other was x intersection x square comma xy comma y square or y power n for any n. So the primary component corresponding to the embedded primes are varying, but the primary component corresponding to the isolated component is x itself. So now let us look at some more interesting properties of ideals in Noetherian rings. Suppose I is this is if I is finitely generated, then I contains a power of its radical. If I is finitely generated, then the ideal contains a power of its radical. That means there exists, see I is contained in radical of I, right. So I have I is contained in radical of I, but what this says is that there exists some m such that this is true. This is when I is finitely generated. How do you prove this? If I is finitely generated, I guess I will require radical of I is finitely generated. If radical of I is finitely generated, then I contains a power of its radical. So let this be equal to a1 up to a n. Each element in the radical there exists a power which is contained in I. So this implies there exists k I in n such that ai per ki belongs to I. Now, if I take my k to be summation ki I from 1 to n, then radical of I whole power k will be contained in I, right. How, what is this? See, this will be generated by, radical of I is generated by a1 up to a n. So, whole power k will be generated by, this is span of a1 power r1 up to a n power r n, where summation r I is k. Now, k is summation k I. So, therefore, at least one, for at least one I, r I will be bigger than or equal to k I. So, therefore, for each, therefore, this each element will be in I. Therefore, the whole of this is in I. Okay. So, corollary of this is that every ideal in a Noetherian ring contains a power of its radical. Because in a Noetherian ring every ideal is finitely generated. So, you start with any ideal, its radical is finitely generated, take its radical and take the generators and do this. Okay. Yeah, and another corollary to this is in Noetherian ring, nil radical is nilpotent. Take I to be equal to 0. What is nil radical? Collection of all nilpotent elements. That means set of all n such that x power n is 0, which means radical of the nil radical is radical of the 0 ideal. So, therefore, if I take in corollary, in the previous corollary, take I equal to 0, then in a Noetherian ring it contains some power is contained in some power of its radical is contained in the ideal. Therefore, some radical of I, which is the nil radical whole power something is 0. Okay. Another interesting, at the same time not very difficult, let A be a Noetherian ring and M be a maximal ideal. Then for an ideal I, the following are equivalent. I is M primary, radical of I is M, and this is M power n is contained in I, contained in M. Now, if I is M primary, it means it is primary and it is its radical is M. So, 1 implies 2 is straightforward. Radical of I is M, then of course, I is contained in M and we are in Noetherian ring, therefore, every ideal contains a power of its radical. So, therefore, M power n is contained. Now, suppose M power n is contained in I, contained in M. We want to prove I is M primary. This equation says that apply radical on this equation. What do you get? Radical of M power n is contained in radical of I is contained in M. Now, what is radical of M power n? M itself, right? Because for M power n, M is the only ideal, maximal ideal containing M power n. So, therefore, M power n, radical of M power n, which is M, M is contained in radical of I contained in M, which means radical of I is M. If radical of I is a maximal ideal, then it is primary. This is what we proved sometime. So, that proves 3 implies 1. I will leave it to you to complete that. Now, let us go ahead and learn some properties of Artinian rings. So, let us recall a ring is Artinian if every descending chain of ideals terminate, that is, if I1, I2 is a chain in A, chain of ideals in A, then there exists K such that I n is I n plus 1, so on. Okay. When we talk about Artinian rings, one important property that we proved earlier is that this is recall. Suppose A is a ring such that the 0 ideal is a finite product of some maximal ideals of A is a ring whose 0 ideal is a finite product of maximal ideals of A. Then A is Noetherian if and only if it is Artinian. This is something that we proved some time back. So, if this is M1 up to, if I can write 0 as M1 up to Mn, then I have a chain product M1 up to Mn contained in M1 up to Mn minus 1 contained in M1 up to Mn minus 2. Each quotient is a vector space over A mod corresponding Mi. So, now by induction we can say that each module, I mean each ideal product is as a module over A, it is Noetherian if and only if Artinian, and by induction we prove ultimately reach M1 and then A. Okay, that's how we proved this result. Now, Artinian rings are and all the examples that we looked at, they are all very close to being Noetherian, or even stronger than being Noetherian. So, we will see that is it is true in general, but before that let us look at some nice properties of Artinian rings. In an Artinian ring, every prime ideal is maximal. Suppose I take a prime ideal, let A be an Artinian ring and P be a prime ideal of okay. We want to say that P is maximal, or in other words we want to say that A mod P is a field. Okay. So, let B be equal to A mod P. We want to say that B is field. We know what we know is that B is integral domain. Now, we also know that B is Artinian because A is Artinian and P is an ideal in A, therefore, B is Artinian. So, B is an Artinian integral domain. We want to say that B is a field. So, let us start with a non-zero element B. Okay. Then we have then there exists this chain, the chain x contained in x square, contained in x cube and so on. That means, since B is Artinian, there exists some n such that x power n is equal to x power n plus I for all I bigger than 1. So, I can write x power n is contained in the ideal general plus 1, or in other words, so I can write this is equal to r times x power n plus 1 for some r in B. Now, B is an integral domain. So, therefore, I can cancel x power n. That means, since B is an integral domain, one is equal to R x. That implies x is a unit, and that implies B is a field. And that is exactly what we wanted to prove. So, what we have proved here is that an Artinian integral domain is a field, and this can be thought of as a corollary to that result. An Artinian, the proof is, if you start from here, what we have proved is an Artinian integral domain is a field, and this is in fact a corollary of that result. So, in an Artinian ring, there are no non-maximal prime ideals. every prime ideal is maximal. Now, equally interesting property of Artinian ring is that there cannot be too many of them. That is, there exists in an Artinian ring there exists only finitely many prime ideals or maximal ideals. Now, I will write it as maximal because there cannot be too many of them. Okay. For this, look at this set. Consider the set sigma equal to m1 up to mn okay, set of all, I will write in words, that is easier to, finite intersection of maximal ideals. I take some finite maximal ideals, intersect and put them in this. This is certainly a non-empty set. I would assume that it is not a field. I am starting with an arbitrary Artinian ring. So, therefore, every collection of ideals has a minimal element in Artinian ring. In Noetherian ring, any collection of ideals has a maximal element. Here in Artinian ring, any collection has a minimal element. Then sigma is non-empty and sigma has a minimal element. So, I will denote this by m1 intersection mn. Okay. Now, I take any other maximal ideal, let m be a maximal ideal. Then this m intersection m1 intersection mn, this is an ideal that is contained in m1 intersection mn. This is, which means this is smaller than the minimal. It cannot be, because this is indeed the minimal. So, therefore, these two are equal. This implies this is equal to m1 intersection up to mn. So, this is an element in sigma and this is contained here, but then this is contained in, if there is a comparison between two ideals, then this is contained. So, therefore, these two are equal. That implies that m contains m1 intersection mn. I intersection j is equal to I if and only if j is contained in j contains I. Okay. So, therefore, this m contains m1 intersection mn, but when a prime ideal contains a finite intersection, one of them is contained here. This means that m contains mi for some I. but that means M is equal to M I. So, if M is any maximal ideal of A, it has to be one of them. That means the only maximal ideals here are M1 up to M. Okay. So, that proves that it has only finitely many maximal ideals. Now, yeah, more properties of Artinian rings I will take up on in the next class.